Hi, today we are going to discuss some of the points related to symmetrical and unsymmetrical faults. You know, any failure which interferes with the normal flow of current is denoted as fault. Fault can be classified as series fault or shunt fault. Shunt fault includes line to ground, line to line, double line to ground, then three phase fault. And series fault include one open conductor fault, two open conductor fault, etc. And among the faults, three phase fault occurs 5%, and most occurring fault is line to ground fault. It is 70%. This is another classification of fault. This is important. That is symmetrical fault and unsymmetrical fault. The symmetrical fault includes three phase fault, and unsymmetrical fault includes the other classifications. That means line to ground, and double line to ground. We have to analyze the symmetrical and unsymmetrical fault. Symmetrical fault means a fault involving all the three phases, and a fault involving only one or two phases is denoted as unsymmetrical fault. The majority of faults are unsymmetrical. For the unsymmetrical fault, we use network reduction techniques. That is, we have to first draw a single line diagram of the complete network indicating the components, rating, voltages, resistance, and reactance. Then we have to choose a common base kVA or base MVA. Then we have to convert all the resistance and reactance in per unit values, which is referred to the common base kVA or base MVA. From the single line diagram, we have to draw a reactance diagram or impedance diagram showing only one phase and neutral. And in this diagram, we have to write the reactance or impedances of the elements in per unit values. Then finally, we have to reduce the reactance diagram by network reduction techniques and to find the reactance of the system as seen from the fault point, which is denoted by the Thevenin reactance. Then next step is to calculate the fault current and fault MVA in per unit and convert these per unit values into actual values. The main formula in the three phase fault or symmetrical fault is indicated in the left side, that is per unit fault or short circuit current equal to per unit voltage at fault point divided by per unit equivalent reactance or equivalent reactance in per unit. Then per unit fault level in MVA is equal to root 3 per unit fault current into per unit source voltage. This is to find the fault level. Fault level means MVA rating, short circuit MVA. Another formula is either we have to solve problem in these two steps or we have to solve problem in another two steps. Either one method should be applied. That is fault MVA equal to base MVA by per unit X equivalent, that is equivalent reactance in per unit. Fault current equal to fault MVA into 10 raised to 3 divided by root 3 into base kV. So these two formulas are important. We can solve one problem. A three phase fault, 10,000 kVA, 11 kV alternator has a subtransient reactance of 8%. A three phase short circuit fault occurs at its terminals. Determine the fault current and fault MVA. So the two methods are explained here. The first method indicates to find the per unit fault current, then fault current equal to and fault power equal to. The values are indicated, that is 125 MVA. This is the alternative method, that is fault MVA equal to base MVA by per unit reactance. Base MVA is given the kVA rating is 10,000, so MVA is 10,000 into 10 raised to minus 3 divided by the per unit reactance, that is 8%. So we get the fault MVA. The next step is fault current. Fault current equal to fault MVA into 10 raised to 3 divided by root 3 into base kV. Base kV is 11 kV. And whatever be the method, the final answer will be the same. Then another problem. There are many problems in this test. This is a course in electric power by J.B. Gupta. A three-phase transmission line operating at 10 kV and having a resistance of 1 ohm and reactance 4 ohm is connected to the generating station bus bars through 5 MVA step-up transformer having a reactance of 5%. The bus bars are supplied by 10 MVA alternator having 10% reactance. Calculate the short circuit kVA fed to symmetrical fault between phases if it occurs. The two cases, one is at the load end of the transmission line and another is at the highest voltage terminals of the transformer. This is the transformer 5 MVA RT, and there are two cases. This is a step up transformer, so this portion is the high voltage side and this part is the low voltage side. We have to solve the two cases, that is the short circuit kVA fed to symmetrical fault between phases if it occurs. One is at the load side or load end of the transmission line, it is denoted as F2, and another is the high voltage terminals of the transformer, it is denoted as F1. So as I mentioned, we have to convert all the reactance values into per unit. That means we have to first choose the base MVA. Here the base MVA is taken as 10 and per unit reactance of alternator, then per unit reactance of transformer, then per unit impedance of the transmission line. All these have to be find out. The formula is ZPU new equal to ZPU old into kV old by kV new the whole square into MVA new by MVA old, that formula. And substituting all these values for all these parameters, we get the per unit reactance of alternator, then transformer, transmission line. For the transmission line, actual impedance is given. We have to calculate the base impedance, and next we have to substitute the actual impedance by base impedance. This is the reactance diagram. The voltage source is taken as 1 angle 0 or 1 per unit. This is the reactance of alternator, transformer, then transmission line. For the transmission line, the value is 0.1 plus j 0.4 per unit. It consists of a resistive part and inductive part. This resistive part is indicated as 0.1 per unit and reactance part is indicated as j 0.4. This is the reactance diagram. We have to consider the two cases. One occurs at the high voltage side of transformer and the other at the load end of the transformer. For a fault at the load end of the transmission line, that is this point, our procedure is to calculate the total equivalent reactance as seen from the fault point. So whenever we saw the total reactance at this fault point, we get the total equivalent reactance as the summation of these four reactants, that is indicated as this value. Then fault MVA or short circuit MVA have to be found out. That is fault MVA equal to base MVA by per unit equivalent reactance or equivalent reactance in per unit. Answer is 16,440 kVA. And for the fault occurring at the high voltage terminals of the transformer, that is this point, so the reactance to be added is these two values, and finally we get the fault MVA or short circuit MVA. This is the procedure. And the analysis of symmetrical fault is like this. Next we have to solve unsymmetrical fault. Here the fault current is not the same in all the phases. The analysis is done by using a special method called method of symmetrical components. As a result, we get the three components: positive sequence component, negative sequence component, and zero sequence component, because any unbalanced three-phase system of sinusoidal quantities can be resolved into three balanced system of phasors called symmetrical components. One is the positive sequence, other is the negative sequence, and third one is the zero sequence. Here we define an operator A. The value of A is minus 0.5 plus j 0.866. A square is minus 0.5 minus j 0.866. A cube is 1. And 1 plus A square equal to 0. This point. And we can represent the unbalanced vectors in terms of symmetrical components, that is VA equal to VA0 plus VA1 plus VA2, VB equal to VB0 plus VB1 plus VC1, then VC equal to VC0 plus VC1 plus VC2. Here a small mistake, VB equal to VB0 plus VB1 plus VB2. And after substituting the values, we get VA, VB, VC equal to 1, 1, 1, 1 A square A, 1 A square, VA0, VA1, VA2. Again I am repeating, the value of A is minus 0.5 plus j 0.866. And we can represent symmetrical components in terms of phase values. This is the representation. VA0, VA1, VA2 equal to 1 by 3, 1, 1, 1, 1 A square, 1 A square A, VA, VB, VC. before going to the analysis of unsymmetrical fault, we have to know the sequence impedance and sequence network. Sequence impedance means impedance offered by the circuit elements to the sequence current, which is positive sequence current, negative sequence current, or zero sequence current. And sequence network is the single phase equivalent circuit of power system formed by using the impedances of any one sequence. And sequence impedance Z0, Z1, Z2 equal to 1 by 3, 1, 1, 1, 1 A square, 1 A square A, ZA, ZB, ZC. We have indicated the voltages in the previous case, the same expression, only the impedance is represented here. Then sequence impedance and sequence network of a generator. Consider this figure: EA, ZA, IA, EB, ZB, IB, EC, ZC, IC. This generator is grounded through a neutral impedance Zn. Zn is the neutral reactance. Z1 is the positive sequence impedance, Z2 is the negative sequence impedance of generator, and Zg0 is the zero sequence impedance of the Z0 is the total zero sequence impedance of the generator. Zg0 is the zero sequence impedance of the generator. So Z0, that is total zero sequence impedance, equal to Zg0 plus 3 Zn. That will be explained later. First we have to indicate the positive sequence components. Positive sequence voltage is indicated by VA1 equal to EA minus IA1 Z1, and that means it is represented by a source EMF on no load and positive sequence impedance Z1 in series with it. Here the neutral impedance does not appear because the phasor sum of IA1, IB1 and IC1 is 0, and no positive sequence current can flow through the neutral or neutral impedance. We have considered the circuit as a balanced circuit. So it is indicated by VA1 equal to EA minus IA1 Z1. In problems, we usually take the value of EA as 1 angle 0 per unit. For the negative sequence part, there is no EMF, so that EMF part is 0, and the voltage is, negative sequence voltage is represented as VA2 equal to minus IA2 Z2. IA2 is the negative sequence current and Z2 is the negative sequence impedance. And finally, the zero sequence representation. Now, for the zero sequence representation, we have to consider the neutral, and for a balanced circuit, the summation of three currents IA, IB and IC will be the 0, and no current flows through the neutral. That is for a balanced circuit. But for an unbalanced case, the zero sequence effect or zero sequence impedance or zero sequence voltages will appear, because the three currents are not balanced. As a result, current will be flowing through the neutral, and the zero sequence network involves the flow of current through the neutral. This flow of current is indicated as zero sequence current IA0, and the value is represented as zero sequence impedance value is represented as Z0 equal to Zg0 plus 3 Zn. where ZG0 is the zero sequence impedance of the generator, Z0 is the total zero sequence impedance, and Zn is the neutral impedance. Here also no EMF source, so Va0 equal to minus Ia0 Z0, and Z0 equal to Zg0 plus 3 Zn. So these two concepts, that means the concept of phase over operator A, concept of positive sequence, negative sequence, and zero sequence network and impedance in the case of a generator will have to be known for solving the analysis of unsymmetrical fault. So first we have to analyze the unsymmetrical fault single line to ground. Single line to ground fault, where the fault impedance is denoted as ZF, and we know a phase, suppose this phase A becomes a faulty condition through this fault impedance ZF. Therefore, the voltage of this phase A with respect to neutral VA equal to 0, and as a result, the current flowing through the other two phases will be 0. All the currents will flow through this faulty portion, that is IB equal to 0 and IC equal to 0, already VA equal to 0. Then the voltage across the fault point VF equal to IF into ZF. This is the diagram. Voltage across the fault point with respect to this ground VF equal to IF into, IF is the current flowing through this fault impedance, into ZF. And IF equal to IA. So by solving the sequence network, that formula as already I mentioned, IA0, IA1, IA2 equal to 1 by 3 into 1, 1, 1, 1 A square A, 1 A square A, IA0, 0, because IB equal to 0, IC equal to 0, we get the important expression IA0 equal to IA1 equal to IA2 equal to 1 by 3 IA, and by solving this equation we get VA equal to 3 IA1 ZF, and finally we get the expression fault current IF equal to IA equal to 3 IA1, that is 3 EA divided by Z1 plus Z2 plus Z0 divided by 3 ZF. If the fault impedance ZF is 0, then fault current IF equal to 3 EA divided by Z0 plus Z1 plus Z2. Again, Z0 equal to Zg0 plus 3 Zn. And this is a positive sequence network, this is a negative sequence network, and this is the zero sequence network. Positive sequence current is IA1. Negative sequence current is IA2. Zero sequence current is IA0. These three reactances are connected in series because we have already derived IA1 equal to IA2 equal to IA0. This is expression IA0 equal to IA1 equal to IA2. And whenever the currents are equal, we know the reactances are connected in series. Next we will discuss line-to-line fault. A line-to-line fault occurs at phase B and C. The generator neutral is assumed to be grounded through the impedance, and suppose a fault occurs between these 2 points or these 2 phases B and C, then current through the phase IA equal to 0. Current through the A phase is 0, that is IA equal to 0, and fault current IF equal to IB. As a result, IC equal to minus IF, or IB equal to IF, which is equal to minus IC. And voltage of fault VF equal to VB minus VC, the difference of voltages in these two phases B and C, because voltage of phase B is VB and voltage of phase C is VC, and fault occurs between the phases B and C through the fault impedance ZF. Again, we are using the concepts of symmetrical components. IA0, IA1, IA2 equal to that matrix. IA equal to 0, IB, I represent IB, IC minus IB. By solving the equation, we get the expression. Similarly, for the voltages VA0, VA1, VA2, and we have to take the concepts of A operator that already I have mentioned. 1 plus A square equal to 0. The value of A is minus 0.5 plus j 0.866. A square is minus 0.5 minus j 0.866. A square minus A equal to minus j 1.732, and A minus A square equal to j 1.732. This 1.732 can be represented by root 3. So by solving the expression, we get the final expression. IA1 equal to EA divided by Z1 plus Z2 plus ZF. The fault impedance is 0, then IA1 equal to EA divided by Z1 plus Z2. Sometimes the phases are directly connected, not through the fault impedance. In such case, the value of ZF is 0. And based on this, we can draw the sequence network. Also, the difference in voltage VA1 minus VA2 equal to IA1 ZF, or VA1 equal to VA2 plus IA1 ZF. Based on this expression, we have drawn the sequence network VA1 equal to VA2 plus IA1 ZF. The another portion, double line to ground fault. Consider the circuit. The difference is the two lines are shorted fault occurs between the two phases P and C, and similarly at the same time the fault occurs through the ground also. This portion ZF is directly connected to the ground. So here also Ia equal to 0. This fault current IF equal to IB plus IC. The difference in voltage VB minus VC equal to IF is ZF, and IF equal to IB plus IC, because the two phases are directly connected, and also it is connected to the ground by means of fault impedance ZF. Again the same expression, we have to determine the values of Ia, IB, IC and VA0, VA1, VA2. The same logic that we have mentioned earlier. We get the expression as VA0 equal to VA1 plus 3 IA0 ZF. This is useful for drawing the sequence network. VA0 equal to VA2 plus 3 ZF. VA0 equal to VA1 equal to VA2. So because these two are connected in parallel, and VA0, this voltage equal to VA2 or VA1, because two voltages are equal, plus 3 IA0 ZF. Based on this, we can draw problems. The problems are direct substitution. It's the direct substitution of these voltage values. So this is a simple analytical representation of unsymmetrical fault. So the conclusion is, to conclude, the fault can be classified as symmetrical and unsymmetrical fault. Symmetrical fault can be simplified by using the network reduction techniques, and unsymmetrical fault, we have to determine the sequence components of currents and voltages. Then based on the expression, we can draw sequence networks and we can do the calculations. The main reference text is A Course in Electric Power by J.B. Gupta. These problems are taken from that text and some websites. Thank you.